Okay, the topic I'm gonna talk today is depth perception for small unmanned air vehicles using monocular vision. This is the course project for image processing and computer vision. My name is Pan Liu. So, um, the UAVs are under rapid development. Many new concepts, techniques, and methodologies have been developed for unmanned air vehicles in recent years, which bring significant progress to this area. Industries, militaries, and individuals are increasingly using UAVs for applications such as mapping, aerial sensor network, and search and rescue. A basic task of autonomous flight is to autonomously track a predefined path, which requires a well-developed navigation system. Many present navigation systems of UAVs are vision-based techniques to accurately estimate vehicle states. They typically use monocular vision instead of binocular vision due to the requirements of simplicity and loading capability of UAVs. Single camera can provide enough navigation information for autonomous UAV guidance and control. The, the configuration based on monocular vision simplifies the system while providing enough navigation information. When it comes to monocular vision, they can be roughly divided into two groups. The basic idea behind the first group is to use successive camera images to reconstruct 3D information, thereby determining depth information. In binocular vision, two images that are taken simultaneously at distinctly locations are used to estimate depth. In the cases of monocular vision, differences between successive images from single camera are used. In the second group, light field cameras are used for depth estimation. Defocus and correspondence of images are combined instead of using only one to get better estimation. Let's talk about why we need to use the light field camera. The light field camera is designed in the way that the light rays through the main lens center always land on the center of corresponding tiny cameras. As the camera rays is more and more compact, the image resolution can be higher and higher. In other words, more objects, points in space can be represented in an image. When we have enough resolution, a valid image can be obtained. The figure in the right-hand side is the production from Literal company. Okay, let's then talk about the principle of light field camera. The light field camera gives us the opportunity to employ the single lens depth sensing approach yet overcome its drawbacks. The difference between light field camera and a single lens approach is that they use different strategies to retain the direction information of light rays. The method of single lens approach is to block unneeded light rays to allow only one direction's light rays reach the sensor plane. However, the light field camera is to keep light rays in more directions but segregate them by directions before they reach the sensor plane. The figure in the right-hand side shows a 1D example. Right above the sensor plane, there are an array of pinhole cameras. These cameras are so tiny that usually each camera only covers an array of several pixels. In this example, there are only 3 pixels inside each tiny camera. The 3 pixels are denoted as R, C, L respectively. The relative position of them inside the tiny camera are known. H sub C is the height of the tiny camera, and W sub C is the distance of the side pixel from the center. The tiny cameras here are idealized pinhole camera. That is to say, the viewpoint here is a point without geometry dimension. So do the pixels inside the cameras. In this figure, parameter V is the distance from optical axis of lens to the aperture on the blocking plate, and F is the distance between the lens and the sensor plane. The subscripts of these parameters denote that they are associated with R or L pixel, because the 3 pixels in the idealized tiny camera can only receive light rays in 3 specific known directions. All light rays in other directions are eliminated. The intensities of light rays in these directions are recorded by 3 different sensor elements individually. Each sensor element, say RCL respectively, is related to a known direction. It is the major improvement comparing with regular cameras. The intensities are not summed up, and we have directions. By simply compact more pixels inside one tiny camera, more directions are available for us. In current time, which the image is focused on the surface of the camera array, the object point is at the depth we already know. This is because the parameter f, which is the distance between the lens and the sensor plane, and the focal length f of the main lens also is constant and known. According to this equation, depth can be calculated. Let's then talk about the dynamic model of a UAV. The dynamic model of a UAV is derived from the Euler-Lagrange equation. The generalized coordinates for the UAVs are represented like this, where xyz represents the position of the center of mass of the UAV relative to the inertial frame, and the phi theta phi represents the 3 Euler equations, that is, roll, pitch, and yaw angles. Then the Lagrange of the UAV can be written like this. The dynamic model of the UAV is obtained from the Euler-Lagrange equation, which is presented like equation 4, where Q is generalized coordinates and F sub x is a generalized external force. Now the nonlinear model is obtained by substituting the Lagrangian 2 into 3 and decomposing the resulting Euler-Lagrange equation. It can be further rewritten into translation and rotational motion, which are given as equation 9 and 10, where z sub I indicates the z-axis in the inertial frame, and C is a Coriolis matrix, which can be expressed as equation 11. Then let's talk about the depth perception algorithm. The algorithm represented in this paper are roughly summarized as 3 steps as following. In the first step, we need to share the epipolar image and get depth estimation from both defocus and correspondence. The second step is computing the optimal depth and the confidence of the estimation from defocus and correspondence. In the third step, we combine the information from both sides by a MRF global optimization process and get a global depth estimation. The UMAP of a 2D epipolar image is written like equation 12, where L sub 0 and L sub alpha are the input API and shared API by alpha, respectively. By integrating the shared API across the angular U dimension, we can get the optimal alpha with the highest contrast at each pixel. This is achieved by a contrast-based measurement, which is written in equation 13. where n sub u is the number of angular pixels. Then let's talk about the correspondence. In order to measure accurate disparities, the correspondent points need to be identified first. The angular variance for a given spatial pixel is equation 15. However, it can be easily confused if we only do matching on individual points. This is because non-corresponding points may still have high chance to have similar light intensity. Therefore, the strategy of matching small neighborhood of image points is used to ensure an accurate result, which is written in equation 16, where W sub c is the window size. And then we can combine the information from defocus and correspondence. We need to find the alpha, which maximizes the defocus measure while minimize the correspondence measure. And next, we need to compute the confidence of alpha d and alpha c by using the peak ratio, which is equation 18, where alpha star square is the next local optimal value for or the next largest peak or dip. And this is the result. In this paper, we use a neutral light field camera to capture the images, which, as discussed above, include different points of view. The output of neutral camera are not accessible images. Further work needs to be done to convert the raw data from the camera to visible images. Figure 6 shows one of the image, which is from the center view, and Figure 7 shows the depth estimation from the defocus information. In this image, the darker in color indicates the closer in distance. As discussed before, this image is consistent but tends to be blurry. Figure 8 shows the depth estimation from the correspondence information. This image produces sharp results but tends to be inconstant and noisy places. In order to get a more accurate depth estimation, we combine the defocus and correspondence information by keeping their advantages and removing their disadvantages. Figure 9 shows the result of this combination. Then we have the conclusion that because the light field camera uses single lens and a single sensor plane, there is no need to calibrate the relative locations and rotations among different cameras like in multi-camera stereo system. This is a great advantage for light field camera because in multi-camera stereo system, much effort needs to contribute to the calibration. Another advantage, as mentioned, is that ambiguity in correspondence problem is minimized and even avoided in light field camera. These advantages make light field camera a broad potential application on UAVs. The method presented in this paper combines the information from both defocus and correspondence to achieve a better depth estimation. This method is relatively simple and computational efficient. Okay, that's all for today. Thank you for watching.